Holcomb. She obtained her bachelor's degree in astrophysics at Rice University. Then she went on to do a pre-doctoral fellowship at the Center for Computational Astrophysics at the Flatiron Institute. And she's now a sixth-year PhD candidate at UC Irvine, where she works with Paul Robertson on topics related to RV, radial velocity exoplanet survey, stellar rotation, and M-dwarf activity. And today she will tell us about rotation and spots. So take it away.
Right, it's a pleasure to be here. Out of curiosity, how many people in this room are exoplanet people? And how many people here are stars people? And how many people? Both? See, that's what I am. And how many people are just, something else in astrophysics? Fabulous. Well, hopefully have a little something for everyone. I always like to start my talks with this quote here that says, Fred Hoyle once started a talk by saying, oh, basically a star is a pretty simple thing. And from the back of the room came the voice of R. Redmond saying, well, Fred, you'd look pretty simple too from 10 parsecs. I like to start this because I think as astronomers, we're often tempted to simplify our systems to look for beautiful, elegant solutions, especially when it comes to stars. We all know the equations of stellar state, but the more we embrace that complexity, the more new science there is to be found. And so that's why I say I do exoplanets when I spend a whole lot of time looking at stars. So what do? I have my fingers in a lot of different pots. I do a lot of work with stellar rotation on TESS. My home group is an RV exoplanet group. We do a lot of RV surveys. We also study a lot of M-dwarf activity with RVs. And I am a member of the Pandora science team. I'm not going to talk about this middle one very much today because I don't have a ton of time, but we will talk about both Pandora and stellar rotation, and you will know when we're doing one because the slide format changes. So, but I do want to say one thing about RVs, which is that I have worked on a couple really interesting systems, including this one, the TOI 1136 system, which has 6 mini-Neptunes in orbital resonance with each other, all inside the orbit of Mercury. So I just kind of wanted to throw it up there. If you're interested in individual exoplanet systems, come find me and talk outside of the seminar. I would love to talk about it more. Also, that's some of my art, so, like putting that up there. All right, well, let's get to the meat of this. Part 1, Pandora. Big science with a small sat. How many of you here have heard of the Pandora mission? Okay, this always happens. It's awesome, so I'm here to tell you about it. What is Pandora? Well, we're going to be doing atmospheric transmission spectroscopy, which some of you may be familiar with. It's essentially a differential measurement where you look at the spectrum of a planet as it transits the star in comparison to just the star's just the star's spectrum, And by doing a differential measurement of these two, you should be able to back out the planetary spectrum. But, as you might guess, this is hard. Stars are big and bright, planets are small and dim, and there are a lot of complications. One of the big ones is that stars are not homogeneous light sources. They have spots, they have faculae, and if you don't take that into account, you can find yourself running into false positive detections of things like molecular lines, especially around M-dwarfs, which have cool atmospheres where you can actually have water and CO2 lines in the M-dwarf atmosphere. And so we need a way to disentangle this. We need a way to know whether that signal is coming from the star or coming from the planet. So that's what Pandora is going to do. We have 2 main mission goals. And actually, the first one isn't about the planets. The first one is about the stars. We want to determine the spot and faculae covering fractions of low-mass exoplanet host stars. And then once we figure that out, then we want to go in and we want to measure the atmospheres of these planets with confidence. So how do we do that? Well, Pandora has 2 main instruments on board. It has a visible photometer, and it has a near-IR spectrograph. There's something I also want to emphasize. I had to cut this slide. But when I call Pandora a SmallSat, I really mean that. This is a new class of NASA mission. It's going to be launching in late 2025. The entire mission has a 5-year development timeline, and it is launching and operating for under $20 million. Compare that to something like TESS, which was, I believe, $200 million, and then something like the big flagships, which are multi-billion-dollar messages. This is really an experiment in doing cutting-edge science with a much smaller budget, a much tighter and more agile team, and hopefully it all pays off. So, we have our visible photometer, we have our near-IR spectrograph. The idea here is that as our planet transits the surface of the star, we're going to be able to tell when it crosses a spot or an active region. Because that photometer, we will see dips in the light curve, and at the same time, we'll be able to monitor the changes in the stellar and planetary combined spectrum. The bandpass of this is very similar to, it essentially is the James Webb NIRCam bandpass. It's also very comparable to the Wide Field Camera 3 on Hubble. So excellent points of comparison when we are looking at these well-known targets. Speaking of which, the observing strategy. Pandora has a 1-year prime mission. We have a primary target list of 20 targets, which are all bright, nearby, mostly M and K dwarfs. We will be having a few more solar-like stars, but we're really focused on those young, active stars, and we're targeting ones that have high levels of activity. The whole point of this mission is figure out how to deal with active stars. So we're not even bothering with some of the quiet ones. We actually really want to get those spots and see what those spots look like. Each of the targets, we will observe 10 transits, and each transit will have a 24-hour baseline. The idea here is to get a really nice, long, out-of-transit baseline that we can use to do a really good disentanglement of the stellar surface and the planetary atmosphere. We also have a backup target list of 20 targets, which we are expecting to dip into a fair bit. Hopefully we will be able to get through all of 40 targets in the prime mission. And there is a chance for an extended mission, assuming everything goes well. That's not currently approved, but people are very optimistic about it. A quick comparison to other missions. Here we have a comparison of the band passes. So you can see Pandora is simultaneously hitting that visible and that near IR. It has a large overlap with James Webb. Yeah, and also the timeline, it will be operating contemporaneously with James Webb. We really view ourselves as kind of a James Webb support science mission. We're trying to figure out how can we do a better job reducing James Webb data. We will be observing some of the same targets. But the nice thing is we are a dedicated exoplanet mission. We do not have to share time with any other science case. We can spend 100% of our time going after these transits. What do I actually do on the Pandora mission? This is my one slide to kind of be like, woo, before we move on to the next thing. I am part of the data pipeline, Data Processing Center, DPC. I work under Christina Hedges at NASA Goddard Space Flight Center, and I also work with Ben Horde, who's a postdoc there. My work has been really focused on the software side of characterizing the instrument. So looking at the point spread function, things like aligning the world coordinate system and getting a handle on optical distortions. I have a lot of experience with kind of low-level mission data through this. In reality, it's a lot of linear algebra. This is one of my plots. This is an example of a point spread function fit that I've done. And then this is that same thing in, I should put axis labels on these. This is radius from the center of the point spread function and the log of the flux. And so you can kind of see this very complex PSF that we've come up with that's made up of all these different spline and Gaussian components. And the idea is to make this very flexible, applicable point spread function fitting package that is actually all open source. And if you want to use this for your instrument, it should be flexible enough to use on other things. But it's primarily for Pandora. If you'd like to talk more about data reduction and spacecraft commissioning, come find me afterwards. Cool. I just want to pause briefly. Are there any questions about Pandora? Because we're going to be moving on to the next thing after this slide. No? All right. Onwards and forwards. Part 2, stellar rotation with TESS. This has been one of my other really big research focuses. And let me motivate it for a second. Why should you care about how stars spin? Well, if you study planets, it has huge implications for stellar activity, for how we interpret our exoplanet data. It tells us about the formation history, and possibly even the habitability of our planets. If you study galaxies, stellar rotation is a tracer of stellar age, so it becomes a powerful tool for galactic archaeology and studying young stellar associations and stellar streams. And if you study stellar astrophysics, hopefully I don't have to convince you. Hopefully you already like stars. But perhaps this whole thing will convince you. So I mentioned that stellar rotation is tied to stellar age. There is this subfield called gyrochronology, which is all built around this idea that comes from Skumanich 1972, that as stars age, they shed angular momentum and they spin down. And they actually, main sequence stars spin down according to this very clean power law. This is a plot showing several young clusters. Each color is one cluster of stars that are all the same age. And you can see they trace out these isochrones. And so the more stars we can find that rotate, that we can put on this plot, the more we can create this system for benchmarking how old systems are, which is very powerful for interpreting the galactic environment and the history of star formation, of our galaxy, of our planetary systems. How do we measure it? Well, historically, we would use rotational line broadening, which is hard. You need spectra for this. You need, it's very model dependent. But it becomes a lot easier when you have photometry at hand. stars have spots. Spots are dark, so as those spots rotate in and out of your line of sight, you'll see these quasi-periodic dimmings associated with those spots. And if you can find those, you can find the periodicity and know how fast your star is rotating. This means that once we got our wide field surveys, like Kepler, it's actually started with Spitzer and then with Kepler up, this opened up a whole new field of gyrochronology. This is from McQuillan et al., 2014, which was a big turning point for studying stellar rotation. And you can see we went from having maybe a few hundred rotating stars in the scientific literature to well over 34,000. McQuillan alone published 34,000 of these. And you start seeing these features pop out. We have this kind of characteristic isochrone swoop. We have this pileup of slower rotating old stars right on the upper envelope. And there's this very tantalizing gap right here in the later type stars that hint at a braking mechanism that was before this undiscovered. And people always ask me, is this real or is this a selection effect? It's real. The more we study it, the more it pops out, and the more we find very compelling reasons to think that it is actually probing something in the evolution of M dwarfs.
What's the difference between black and blue?
Let me see. Let's see. So the blue is the McQuillan sample. I believe black are from an older ground-based survey, but I forgot which one. So, obviously the next answer is to go get more data. So Kepler was like, hey, we relayed this great groundwork, what can we do next? And that's where TESS comes in, and TESS says, I got you. Of course, if we want to talk about even more data, there's something even more exciting on the horizon, which is the Roman Space Telescope. I'm putting this up because I'm very interested in working in Roman in the next few years as it launches in late 2026. It's going to be just the galactic bulge survey. We'll be monitoring more than 200 million stars, which means we could go from tens of thousands of rotation periods to tens of millions, literally 3 orders of magnitude. The potential to study the galactic bulge through this is very exciting. So if you want more rotation periods, maybe fund my postdoc. I make this super shameless so I don't get embarrassed telling people that. Moving on. Let's go back to TESS. So I'm guessing most of you have at least some familiarity with the Transiting Exoplanet Survey satellite. It is an all-sky photometric wide field survey that is monitoring about 90% of the sky at super high cadence, either 2 minutes or 30 minutes. But it is limited to these very short observing sectors of about 28 days. But it does enable us to do all sky stellar rotation searches, which Kepler focused on one field. Now we can do a much broader look for them. Comes with a lot of challenges though. It has a very short baseline, so those slow rotators are really hard. It's got a lot of systematics you have to deal with. I mentioned that slow rotators are hard. They're even harder because the pipeline is really built for transiting exoplanets. And so those long-term signals tend to get squashed out in the Spock pipeline. It also has very large pixel sizes, so you get a lot of neighbor contamination you have to deal with too. So it becomes a problem. How do we get rotation periods out of this fantastic data set that is too big to ask one grad student to click through all of them individually? I know, I was that grad student for a while. So, how do we automate this? Well, my answer is a package called SpinSpotter. I published this in 2022. It is an open source software package. You can go and pip install it on your computer right now. And it is designed to search for rotation periods in large photometric data sets. I focused on TESS, but I have used it on Kepler data. And in theory, it should also work on anything that has a high enough cadence that you can kind of bid it to even cadence. It's based on the autocorrelation function, which I personally find more reliable to work with than something like the long Scargill periodogram or other Fourier-based methods, because this is based on star spots, and star spots will change over time. Something that does a global Fourier transform is going to struggle with that changing shape of periodicity, whereas an autocorrelation function is very well suited to deal with these kind of the changes in the shape of the periodicity. I won't spend too much time on how SpinSpotter works because I have a few more things I want to get to. But essentially what we're doing is we're characterizing the shape of the peaks in the autocorrelation function. And we do this to make it very flexible so you can tune it to your science case. We can characterize kind of the height, the width, kind of the parabolaness by fitting an R² to it. And of course then we can get the rotation period out of it. And then apply these various cuts to say, okay, how stringent do we want to be on accepting, it's kind of a trade-off between false positives and false negatives. How stringent do we want to be? And when you apply that to the whole test sample, what do you get? Well, you get something that looks like this. I applied SpinSpotter to the entire 2-minute cadence sample up through sector up through all the sectors that were released as of 2022. I forgot which number it stops at right now. This is a comparison of the SpinSpotter sample in blue to the McQuillan sample in pink. That was the one from the graph previously. And if we compare the distributions, we see some really interesting things. For the earlier type stars, you see we nicely trace out the bottom of this isochrone swoop, but we hit this really hard cutoff right around 13 days, which is about half a test sector. There are ways to push to get longer rotators, but it takes, you pretty much can't do it with the spot pipeline. You kind of need your own light for production. There are people working on this. If you need tools to get slow rotators out of tests, come talk to me. I can hook you up with the right tools to do that, but it is a much more difficult, precise treatment you need to do. But something we don't see in the Kepler sample is this huge population of super fast rotating M dwarfs, which is really exciting. A lot of us exoplanet people are very interested in these M dwarfs. A lot of these are very active, so they make for great studies for stellar activity and other types of, stellar astrophysics. And so we kind of have this ready-made set for anybody who wants to go study M dwarfs. And indeed, I have used SpinSpotter to help people do survey selection for their follow-up M dwarf surveys. And it's been very successful at that. Yeah, so it's kind of, once again, if you need to find rotation periods, try installing SpinSpotter. And you can also email me if you run into any bugs, because I'm still actively supporting it and intend to be for quite some time. Now I'm going to sneak in my secret part 3, which is, okay, I've made this cool rotation pipeline. What comes next? Well, the answer is, what comes next is collaboration. This is a picture from the 50 Years of the Skumanish Relationship Conference back in 2022. This was an entire conference dedicated just to stellar rotation. And what we realized when we all got there in a room together is that there were a ton of people working on this, and there are a ton of fantastic tools out there. This is not all of them. This is a small selection of open source FFI and light curve tools and rotation pipelines and catalogs. And you can see there's people using all sorts of different methods. There's people using all sorts of different population cuts and FFI reduction. And you sort of run into this question where, okay, we have all these great tools. What do you use for what situation? And that's something that we need to start tackling. How good are we holistically at measuring rotation periods? What sort of blind spots do we still have with tests? Are there any inherent limitations with the spacecraft and the survey strategy that we need to push past? And if you want to use one of these tools, which one do you start with? What's right for your science? So we need a way to compare all these methods. And that is what I'm trying to do. This is called the test rotation collaboration. And the idea is basically get all the rotation people in one room and talking to each other. And we're doing it by way of a data challenge. So essentially what I'm doing is I'm creating a simulated data set of test data products with injected rotation periods, so we know the ground truth. And then I am inviting people to run their rotation pipelines on it, and then we can kind of homogenously compare how our pipelines perform. And we're really interested in answering a couple of these goals. First of all, having a well-established framework so we can understand what methods work best in different parts of the parameter space. We want to evaluate the current state of our overall ability to measure rotation with tests, so we know how well are we doing and what mountains do we still have left to climb. And we want to be public-facing. We want to be a user guide to the community, so that way if you're coming here from outside of stellar rotation, it's easier for you to get your hands on the best tools for your science. This is the timeline of how it's working. It's kind of a 5-step process. So I initially reached out to people who I knew were working on this. I also went through the literature, reached out to people who had papers on stellar rotation to see if there was enough interest in a project like this. I got a fantastic response. I actually had multiple people be like, I've thought about doing something like this in the past. I don't have time, so I'm really glad somebody's doing it. There's also a great I had to cut the slide, but there's a great precedent where Suzanne Agrin in 2015 ran a very similar data challenge for Kepler that proved very useful in evaluating different stellar rotation finding methods. So step 1, make sure there's enough interest. Thumbs up on that. Step 2 is the generation of the data set. This is something that I am currently working on. I have a package called SET, which is Test Backwards, Simulated Sky Exposures of Tests, where I'm creating the simulated test images, including test systematics, and injecting the simulated light curves. Next, we will be distributing the data to teams and give them some time to analyze it, at which point they will give their results back to me, and we'll kind of perform a meta-analysis, which we will then write up and publish. The timeline for this is unfortunately had to be pushed back a little bit because I started working on the Pandora team, and so I have had to put the collaboration part of it on hold until my work on Pandora is wrapped up, which will be happening soon. But we're hoping to distribute the data to teams in kind of spring to summer of 2025, get the analysis back by the fall, and be putting this paper together towards the end of next year. I won't get too into this, but if you're interested in how I'm generating the simulated data set, I've got a whole flowchart and pipeline. It is all simulated, but all the simulated images are based on real test fields. So we're using the input catalog to know where to inject sources. We're using the test PSF to make sure that we have accurate crowding. And we are including systematics like the velocity drifts and the sector-to-sector offsets that you run into. The key questions we want to answer are, first of all, what are the methods that give us the highest accuracy when it comes to accurately identifying which stars are rotating and what the rotation period is? And also, which ones give the highest yield? So if you want to get down to those very low signal-to-noise rotators, what's the best tools for that? We want to benchmark kind of how accessible these methods are. Do you need a cluster to run this? Can you run it locally on your laptop? Is it open source? Is it well supported? We want to understand how it works if you're working with spot pipeline products, whether going back to the full frame image and doing your own reductions. We also want to really study this in the regime of slow, medium, and fast rotators. Trying to pull slow rotators out of TESS is a very different problem from trying to find fast rotators. And we really want to highlight which methods are succeeding in which areas. And we want to kind of determine the overall recovery rate of rotators from TESS. This will help us understand kind of on a population level how well we can represent the population distribution of stellar rotation from the data set taken by TESS. I just want to highlight a little bit who's involved. These are the logos of some of the teams who have either contributed to the creation of the simulated data set or have indicated an intent to participate in the data challenge once the data becomes available. So you can see it's really a global effort. People are working on this problem all over the world, and I'm really excited to be a part of bringing all those people together in conversation, knowing that we can do more when we work together. If you want to get involved, so if you have a stellar rotation pipeline, or you know someone who does, or you just want to use the data when it's done, I would love to get in contact. I have a QR code. You can also email me directly. And we're really just looking to get everyone in the loop who wants to be in the loop. It's a collaboration. We would love to have you. And that's my last slide. So I can take time for questions now. Happy to answer questions about rotation, about Pandora, or getting in contact about any of this stuff. Yes?
So I'll ask one about, you had the figure of the light curves that include your rotation periods for the pile of M stars there. So there are two questions. One, you argued that the McClellan pile up there was possibly related to the sector observation length.
Oh, that's the pile up in mine. So you don't see that pile up in McClellan. McClellan,
Oh, sorry.
gets to long rotators. Yeah.
But to get around that, can you test the sample on the polar region where you have the very long observations, so you're basically unbiased against your sampling frequency?
Yes.
And you can basically say this is the ground truth. Anything varying off that is because of our limitations of our window function.
Yeah, so there are a few papers out that really go after these slow rotators, and they usually do it in the continuous viewing zone. Sorry, one moment. The paper I usually point people to is Clater et al. 2022. The problem is that even when you have these continuous sectors, TESS has a pervasive problem where adjacent sectors will be offset from each other. And when you're looking at these very long-term trends, I'm so sorry, something in the air. When you look at these long-term trends, it becomes difficult to know what is like a spacecraft instrumental trend that you need to flatten out, and what's a real trend that's part of a very, 100-day sinusoidal thing that just looks linear when you take a slice of it. So it becomes this very difficult degenerate problem. Hattori also has a pipeline called Unpopular that looks for rotation periods at the same time it does the sector-to-sector stitching, and he's been able to pull out some of these very, very slow rotators. But you do have to be very careful to make sure you're not leaving in spacecraft systematics, but not taking out rotation periods.
I just had a question on that pile up on the M dwarfs.
Mm-hmm.
And that's because this sample has more M dwarfs in it?
Yeah.
Yeah, and then, so
goes up to 10 days period, and then it's sort of near your cutoff, sensitivity cutoff. So is that selection
Yeah, so
real in some sense, or would there be that population would continue up to the slower rotators if you have better sensitivity?
it would, and we actually do see this in ground-based surveys. So ZTF has a long-term ground-based photometric survey, and they have some of those slow-rotating M dwarfs, and it's really interesting. So you see this isochron swoop, and then it kind of diverges. So you get this huge vertical scatter in the M dwarfs. So you have some very, very fast-rotating ones. You also have some very slow-rotating M dwarfs. And that's because the Skumanich spin-down lock kind of breaks down as you get to fully convective M dwarfs. And so, yeah, you would see that continue up. And there's some very interesting stellar astrophysics in that.
Any other final quick questions for Ray before we move on? And before the place burns to ashes, given the smell that we're all getting. All right, well, let's thank the speaker again. Thanks very much. All right, so I'm happy to introduce the second speaker of the seminar today, Yuejing Ni. Yuejing is an ITC fellow here at the CFA, and she works on cosmological simulations, in particular understanding things like how large-scale structure impacts early quasar evolution and quenching of star formation in galaxies. Yuejing is also an expert on deep learning applied to cosmological simulations, and she's been particularly interested in applying super-resolution methods based on deep learning to enhance cosmological simulations. She's going to tell us about AGN feedback and quenching in cosmological simulations. Yuejing, floor is yours.
Thank you for the warm introduction. So today I'm going to talk about the modeling of agent feedback and the quenching of galaxies in cosmological simulation. Well, no, sorry. So I'll start with a schematic overview of the cosmic history. With the evolution of the cosmic web, the first stars and galaxies form, and the photons from them enlighten the universe and ionize the neutral IgM gas, the epoch what we call cosmic dawn. And both the star formation and the AGN activity peaks at the epoch around redshift 2, the epoch which we call cosmic noon. And the activity declines gradually after that time. So most of the massive galaxies were star forming at high redshift. A significant amount of them starts to transition from star forming to quiescent during and after the epoch of cosmic noon. And those quiescent galaxies can appear to be very red in the color in observations, and they can be identified in diagnosis like the color diagram as shown in the left upper corner of those plots. And you can see that with the time evolution, a population of the quiescent galaxies start to emerge when going to the low redshift. And when we decompose the population of those quiescent galaxies in the stellar mass, here is a plot of the galaxy mass function divided by the star forming and the quiescent galaxies. We can see that the population of the quenched galaxies dominates the massive end when going to the lower redshift. At the current universe, most of the massive galaxies are already quenched. So there are many physical mechanisms proposed to account for the quenching of the massive galaxies. And they can roughly be categorized on different physical scales. On the largest scale, this is called cosmological starvation, where the IgM gas failed to accrete efficiently to the halos. And on the intermediate CGM scales, where the physical mechanisms like the shock heating, the gravitational heating, or the agent feedback can prevent the cooling of the halo gas to prevent the streaming of the cold gas falling to the central ISM regions. And in the smallest ISM scale, the quenching usually emerge from the physical mechanisms like the reducing the star formation efficiency. This can arise from the the injection of the turbulence from the formation of the stellar bulge or the bar, which is called morphological quenching. So through all those different physical scales, we can see that the agent feedback can play some role there. So actually, there are many aspects in the observations that we need for agent feedback to explain the observed galaxy properties. The first one is we need agent feedback to account for the galaxy luminosity function at the bright end. Basically, the theoretical modeling of the galaxy's evolution without astrophysical feedback will overpredict the abundance of galaxies in both the bright and the faint end. So basically, the gas in the halos form stars too efficiently. So we need some astrophysical feedback process to regulate the star formation in both small mass halos and the large mass halos. While the supernova feedback are able to account for the suppressing of the star formation for less massive galaxies, but the energy from the supernova explosion is not enough to expel the gas from the massive halos, which has huge gravitational potential. Therefore, we need more powerful central engine to regulate the star formation in those massive halos. And that's why most of cosmological simulations need to implement the agent feedback, enable to reproduce the massive end of the galaxy population. And secondly, there's observational hint for agent feedback comes from the galaxy color binodality. So in the current day universe, the galaxies mostly fall into two categories. One is the quenched red sequence galaxies, and the other is the star-forming galaxies, which we call red sequence and the blue clouds. So in this intermediate transitioning state, there is a population called the Green Valley galaxies, which people think it represents the transitioning state from the blue cloud to the red sequence galaxies, where they have recently quenched star formation within a short period of time. And in those population of Green Valley galaxies, there are many agent host galaxies or the secret galaxies in this regime, which implies the agent activities. So this is one observational clue that the agent activity might account for the transitioning of the blue cloud galaxies to the red sequence galaxies. And finally, agent feedback is required to solve the issue of the cooling flow problem in groups and clusters. So the X-ray observations in large groups and clusters implies that there should be rapid cooling flows from the X-ray emissivities. However, the actual observed cooling rate derived from the observation of the cold gas and the star formation is far lower than the prediction from the X-ray observation from the X-ray emissivities. So there must be some energy budget that can counterpart the strong cooling flow in those groups and the clusters. And we resort to the energy from the agent jet, which can be implied from the enthalpy of the X-ray cavities in those X-ray groups. Well, here we see the y-axis is basically the energy budget from the agent jet in those massive clusters, and the x-axis is the implied cooling luminosity. So we need some energy budget to counterbalance the energy loss from the coolings in the clusters and the groups to explain the observation of the actual cooling rate from the cold gas. Therefore, that's why most of the cosmological simulations of galaxy formation need to include agent feedback to explain the many observables. And in cosmological simulations, agent feedback are implemented in a very phenomenological way because it's a very hard problem that bridges over a huge dynamic range. So here is a very brief schematic of how in galaxy formation simulations, how people implement the agent feedback. So it can be roughly categorized in two regimes, the radiative efficient regime and the radiative inefficient regime. At high redshift, most of the agents are accreting very actively in a high Eddington state, and it transfers significant amount of the accretion energy and the radiation, and the strong radiation heats the surroundings of the gas. So in simulations, we mimic this effect of radiative heating through the thermal mode agent feedback, which just deposits thermal energies to the surrounding gas. On the other side, at the late epoch of the universe, most of the black holes or agents are accreting in low Eddington mode. And this mode is dominated by the advection accretion flows, which do not radiate as efficiently as the quasar mode. And the agent in this low Eddington rate regime deposits most of its energy through the kinetic power carried out by the agent jet. And those relativistic jet will emit in the radial band. So sometimes the jet mode is also dubbed as the radial mode. Here I'm showing the illustration of the two-mode feedback from the ASTRID simulation. Typically, the radial mode or the jet mode feedback quench the galaxy way much more efficiently than the other mode. So here we are seeing a zoom-in region from a massive galaxy cluster, and all those orange spikes are the black holes in the quasar mode, and the red spikes are galaxies in the jet mode. And we can see that most of those agents that are operating in the jet mode have already quenched their galaxies, while the other way around, the agents in the quasar mode have the star-forming galaxies. As for a brief introduction for the ASTRID simulation, this is a large cosmological hydrodynamic simulation that I have been worked on for many years. It includes a range of subgrid physics to model the evolution of the universe with high resolution and very large volume. So ASTRID simulation has a box size of 250 megaparsec over H, and represented by particle load of 5,500 Q. And it's run on the Frontera supercomputer and consumes about 700 million CPU hours, being maybe the most expensive simulation field. Here I'm showing some basic statistics of the ASTRID simulation. On the left, we are seeing the statistics of the galaxy mass function compared to observations. And on the right, we're seeing this rising of the quiescent galaxy population when going to lower redshift. We can see that the quenched galaxies, massive quenched galaxies are here. They basically have a very suppressed star formation rate. And if we plot those quiescent galaxies in the scaling relation plane between the M black hole and M star, we can see the effect of the agent feedback. Basically, so here I'm showing the scaling relation between black holes and M star, colored by, on the left, the specific star formation rate, and on the right, the galaxy color. And those populations with redder colors represent the galaxies with lower star formation rate, and the redder color, which are basically quenched galaxies. And we can see that those quiescent galaxies tend to host overmassive black holes compared to the overall population. This indicates that those overmassive black holes tend to exert more powerful agent feedback that account for the quenching for those galaxies. So recent advances in the observations are able to disclose more details of the morphological properties of those quenched galaxies. In particular, people find that there's correlation between the galaxy size and the the age profile. Well, so from the IFU surveys such as Magna, they're able to resolve the radial profile of the galaxy colors, which can, from there, we can infer the galaxy stellar age profile and determine whether the inside region of the galaxy quench first or the outside region quench first. So what they find is that during the among the population of the quiescent galaxies, the one with more compact morphologies tend to have younger stellar population in the center, while the more diffuse, quiescent galaxies with more diffuse morphologies tend to have older stellar age in the center, which we can infer that their central region quench first and their outskirt quench later. So in the ASTRID simulation, we also look into this correlation. Here on the left bottom panel, I'm plotting the galaxy size mass relation colored by the age difference between the inner region of the galaxies and the outer region of the galaxies. The red color indicates the galaxies with older stellar population in the center. So we can see, like along with the observations, the galaxies with more diffuse morphologies tend to have older stellar centers, while the galaxies that are extremely compact, those are quiescent galaxies. The galaxies that are extremely compact tend to have younger stellar centers. And from the simulations, we can pull out or reconstruct the star formation history and the agent activity, which plotted as the inset here. So, looking at their star formation history, we can quantify the time scale where the quenching of the galaxy happens. And what we find is that those diffuse galaxies with older stellar centers tend to also feature a longer quenching time scale, while the more compact galaxies tend to quench very rapidly. So here I'm showing some typical examples for those two populations of the quiescent galaxies. And we're seeing the orange lines showing the star formation history as a function of the look-back time, and the red lines showing the agent activities, the agent light curves. So the physical explanation behind this correlation is that we find that in those very extremely compact quiescent galaxies, they're usually driven by some compaction-like process that efficiently funnels the gas into the central region of the galaxies and incurs the very rapid starburst event. And also those funneling of the gas into the central region also incurs very active accretion of the black holes that build up their mass very quickly and are able to exert very powerful agent feedback that very rapidly quench those galaxies. On the other side, those slowly quenched galaxies are evolved more securely, and their central black holes never experience this phase of very rapid increase with time, and therefore their light curves are also quite flat, as well as the star formation history of the galaxies. The central black holes in those galaxies just gradually releasing the feedback energies and deplete the gas on the galactic scale. The central region of the galaxy quench first with a trace of the star-forming galaxies in the outskirts, and the galaxy is quenched by a gradual depletion of gas. So I have introduced agent feedback implementation in the cosmological simulations. They are able to account for many observational aspects, such as detailed morphological correlation of the quiescent galaxies. However, there are still many challenges that we are not able to resolve. One significant one is that most of the cosmological simulations seems to significantly underpredict the abundance of high redshift quiescent galaxies. So here's a work led by Emma Welder, who was a Harvard undergrad student working with Fabio Acucci and me. We look into the population of the high-ratio quiescent galaxies in both ASTRID simulation and the TNG simulations. We find that while most of those high-ratio quiescent galaxies are quenched by AGN feedback, however, we look at compared abundance of those quenched galaxies to the most recent JWST constraints on the abundance of high-ratio quiescent galaxies. We see that there is like order of 1 to 2 orders of magnitude offset. A solution out to this tension might be that we need to develop a better modeling of the black hole's evolution over the cosmic history to endure more efficient quenching this high-ratio regime. That's like one possible solution to that tension. So in the last part of my talk, I will talk about some limitations of the current agent feedback models. Apart from it underpredicts the high-ratio galaxy quenching, it also have huge uncertainties in the physical scale of the agent energy deposition. So the problem of agent feeding and feedback is a very notoriously difficult problem because it just crosses over huge dynamical scales over 10 orders of magnitude, and there's no way to model it like self-consistently in a fully self-consistently. So simulations adopt a very ad hoc phenomenological modeling of agent feedback, and most of them don't really converge to each other. So here I'm showing a movie from the CAMOS simulation suite for different galaxy formation models, simulating the same box of the universe, same realization of the universe. And what we're seeing here is the gas temperature map with the time evolution. So we see that, for example, the SIMBA simulation, which has very aggressive long-range implementation of the agent feedback, deposit most of its energy in IGN gas and the heat IGN gas very aggressively. While here is TNG and the ASTRID realizations, we can see that the range of the agent feedback is quite local to the halos. So the simulations has a large discrepancy with each other for the predictions of the range of the energy deposition of the agent feedback energy. But why does that matter? Apart from that agent feedback is important for the galaxy evolution, it also has huge implications to the cosmologies. So basically, the agent feedback is very efficient at redistributing the baryonic matter. Here I'm showing the histogram of the baryonic gas displacement. Basically, it's a quantification of how far away the baryonic gas are blown out of the halos and redistributed in the IGN. So we can see that with a very powerful long-range agent feedback implementation, it very efficiently redistributes the baryonic gas on very large scales. And therefore, the overall matter distribution ordered correspondingly. And it has imprint on it has huge effect on the total matter power spectrum. So here we're showing the effect of those astrophysical feedback process on the large scale clustering of the matters. This is the matter power spectrum where the ratio of the matter power spectrum between the hydrodynamic simulation over the dark matter only simulation. And for those different simulation suites, they are based on the same realization, so no cosmic variance here. And we're seeing that this suppression of the matter power on the large scales are brought by the agent feedback we see in the movie before. So this modification of the matter power spectrum due to the baryonic physics which is hugely uncertain because our agnostic of the agent feedback modeling are one of the major systematic uncertainties in cosmological weak linear surveys. So to determine the energy deposition of the agent feedback, it is essential for us to understand how the agent jet comes out of the galactic region, or how it interacts with the ISM. So from the observations, there are recently many observations implying that the agent jet can interact with the ISMs. So for example, here there are some observation of the quenched galaxies in the local universe, observed both in the radial band and in Magda optical band. And they see that there's low far detection of the radial contour, which implies agent activities, are co-spatial with the Magda detection of the very strong H-alpha emission and high velocity dispersions. This implies that there are ionized gas outflows driven by the central agent activities. So as a effort to better understand how the agent jet interact with ISM and propagate out of the interstellar medium region, we work with grad student Olga Borodina, who sits in the audience, carry out those simulation study of the agent propagation within the ISM region. So those are like small central small boxes that mimic the central region of the galaxies with the turbulent ISM driven by the box scale turbulence. And we're launching the agent jets in those boxes. This is a low power agent jet. We can see that not all the agent jets are able to strictly direct out of the ISM region. In this scenario, the compact agent jet got distorted in the morphology, and its propagation got installed by the turbulent ISM. And in some scenarios, it is able to launch the hot gas outflows as observed in the map observations. So here is a brief summary of my talk today, and I will stop here and take questions.
All right. Thank you, Ying, for a very nice talk. Any questions from the audience? Yes?
Yeah, that was super interesting. Thanks so much. I was hoping you could go back to your slide where you showed the star formation history and black hole accretion history of your compact galaxies, and then the ones on the right. So maybe if you could make it full screen again, if that's possible, it's a bit easier to see. So if I understand this correctly, there's some critical time where the star formation in orange just drops to 0.
Yeah.
But the black hole continues to accrete. So some threshold has been passed where gas is no longer converted to stars, but it still makes its way to the black hole. So do you know something about the state of that gas, how that happens?
You mean like this state where the star formation rate drops to 0?
Yeah, because it's a common feature in all 4 of those objects. It's just, to me, that's very interesting.
Yeah, I think in this regime, well, the density of the gas in the central region of the galaxy is so low that it can no longer pass the threshold of the star formation. However, there's still some gas there, so in our it can still accrete onto the black hole. That's why in our model implementation, as long as you have some brownish gas in surrounding the black holes, there's black accretions and yeah.
Okay, is it okay if I ask one quick question?
Go for it.
So as with regards to the very high redshift massive crescent galaxies, how we're finding a lot more James Webb than predicted by the simulations.
Yeah.
So, and you mentioned how it's important that the black holes are seemingly overmassive in the simulations. Do you know how the black hole masses at redshift 4 or 5 massive galaxies compare to what we're finding in the observations? Do we have that information, or is that something that would be useful to compare if we don't have it yet?
I think the problem is that the constraint on the black hole mass function, like at high redshift, is very uncertain. There's basically no very robust constraint on the black hole mass calculation. So we can only compare the luminosity function, which is more certain in the observations. But
Okay, so that's good. As observers, we have more work to do, so that's good news.
More funding. Yes. And
Really nice to talk to you. I'd also have a couple of questions, but the first one is also on this slide. There's a couple of black holes there that are pretty high black hole to stellar mass ratios you have, like 10% upwards. I'm kind of wondering if you found some kind of link between how high that percentage gets to any other property of the galaxy, and kind of when you can get, at what redshift these kind of really quite overmassive black holes far above the local relation kind of start to appear.
I think we definitely find the most significant relation is that overmassive black holes tend to be in the host more compact. So if you look at if you compare the volume 2 panels here, sorry, it's a very messy plot, but the black holes that are approaching like almost 1/10 of the galaxy mass tend to be very small in size.
Okay, so that probably drives the equation. Okay. But the other quick question I had was about, well, hopefully very quick. In ASTRID, there's a kinetic mode now, is there?
Yeah, it's
Is
not
that-
the kinetic,
yeah.
like long chapter.
And kind of at what, does it seem to be a fairly sharp, with the quenched fraction seem to drop quite sharply at above black hole mass about 10 to the 9. I'm kind of wondering what is your switch currently between the modes?
Yeah, it's like few times 10 to the 8.
Okay.
Like 4 times 10 to the 8.
Okay, so is it like a kind of TNG Eddington fraction modified by
Yeah.
black hole mass? Okay, thank you.
all right, unless there is a very quick final question, I think we can leave it there. Let's thank both speakers again. See you in a week. Thank you.
Thank you.